The universe is vast and mysterious, an endless expanse that stretches beyond our imagination. It's filled with billions of galaxies, each containing billions of stars, planets, and countless other celestial bodies. But how did it all begin? What sparked the creation of everything we see around us? The prevailing scientific theory is the Big Bang, a monumental event that set everything into motion. Imagine all matter and energy compressed into a single point, smaller than an atom, a singularity of unimaginable density and heat. This point then exploded, creating space and time as we know it, in a fraction of a second. This explosion, about 13.8 billion years ago, was the Big Bang, the birth of our universe. The Big Bang theory is not just a guess or a wild idea. It's supported by a wealth of scientific evidence gathered over decades of research and observation. We observe the universe expanding, with galaxies moving away from us, like dots on an inflating balloon. This expansion suggests they were once closer together, originating from a common point. The Big Bang model predicts this expansion, aligning perfectly with our observations. Further evidence comes from the cosmic microwave background radiation, a relic from the early universe. This faint afterglow of the Big Bang permeates all of space, a silent witness to the universe's fiery birth. It's like a baby picture of the early universe, capturing its infancy. This radiation tells us the universe was once incredibly hot and dense, a seething cauldron of energy. The Big Bang theory explains this observation, providing a coherent narrative of our cosmic origins. The Big Bang theory doesn't say the universe exploded into a pre-existing space. Instead, space itself expands, carrying galaxies with it. Imagine a balloon with dots on it, representing galaxies. As you inflate the balloon, the dots move farther apart, just like galaxies in our universe. The dots represent galaxies, and the balloon surface represents the fabric of space-time, expanding in all directions. Astronomers have observed this expansion firsthand through meticulous observations and measurements. By measuring the light from distant galaxies, they found that these galaxies are moving away from us, a phenomenon known as redshift. The farther away a galaxy is, the faster it's receding, which is a key piece of evidence for the expanding universe. This observation is consistent with an expanding universe, a concept that has revolutionized our understanding of cosmology. The expansion of the universe has profound implications for our understanding of its history and future, influencing theories about its ultimate fate. It tells us that the universe was once much smaller, hotter, and denser than it is today, a state that existed billions of years ago. It also raises questions about the ultimate fate of the universe, whether it will continue to expand forever, slow down, or even collapse back on itself. The discovery of the expanding universe revolutionized our view of cosmology. It shifted our perspective from a static, unchanging universe to a dynamic, evolving one. This discovery also led to new mysteries. One of the biggest mysteries is the rate of expansion. Scientists expected the expansion to slow down over time due to gravity. However, observations in the late 1990s revealed the opposite. The expansion of the universe is accelerating. This unexpected acceleration suggests the presence of a mysterious force pushing everything apart. This force, known as dark energy, remains one of the biggest enigmas in modern physics. While studying the rotation of galaxies, astronomers noticed something strange. The galaxies were spinning faster than they should be based on their visible mass. This discrepancy suggested the presence of unseen matter providing extra gravity. This unseen matter became known as dark matter. It doesn't interact with light, making it invisible to telescopes. We can only infer its existence through its gravitational effects. Dark matter is thought to make up about 85% of the total mass of the universe. Understanding the nature of dark matter is crucial for understanding the formation and evolution of galaxies. The accelerating expansion of the universe is a perplexing phenomenon. It implies the existence of a force counteracting gravity, pushing everything apart. Scientists call this force dark energy. Dark energy is even more mysterious than dark matter. We don't know what it is or where it comes from. One possibility is that it's a property of space itself, a kind of cosmic anti-gravity. The concept of dark energy has profound implications for our understanding of the universe's fate. Its existence suggests the universe will continue to expand forever, becoming increasingly cold and dark. The future of the universe depends on the intricate interplay between gravity and dark energy, two of the most fundamental forces in the cosmos. Depending on the balance and behavior of these forces, the universe could end up in one of three distinct ways: the Big Freeze, the Big Rip, or the Big Crunch. Each scenario paints a different picture of the ultimate fate of everything we know. The Big Freeze is currently considered the most likely scenario based on our present observations and understanding of cosmic expansion. In this scenario, the universe continues to expand indefinitely, becoming increasingly cold and diffuse as galaxies drift farther and farther apart. Over time, stars will burn out, and galaxies will become isolated in the vast, dark expanse of space. This scenario is sometimes referred to as the heat death of the universe, where all thermodynamic energy is evenly distributed and no significant processes can occur. The Big Rip, on the other hand, is a far more dramatic and violent possibility. If dark energy, the mysterious force driving the acceleration of the universe's expansion, intensifies over time, it could eventually overcome all other forces. This would result in galaxies, stars, and even atoms being torn apart at an ever-increasing rate. This catastrophic scenario would lead to the complete annihilation of all matter and energy, leaving behind a universe devoid of any structure or substance. The Big Crunch is the least likely scenario according to current data, but it remains a fascinating possibility. In this scenario, if gravity eventually overpowers dark energy, the expansion of the universe could halt and reverse, leading to a gradual contraction. The universe would then collapse in on itself, eventually returning to a state of extreme density and temperature, similar to the conditions of the Big Bang. This cyclical model suggests that the universe could potentially undergo endless cycles of expansion and contraction. The Big Freeze is the most widely accepted scenario for the end of the universe. In this scenario, dark energy continues to drive the expansion of the universe at an accelerating rate. As the universe expands, it also cools down. Over vast cosmic timescales, stars will burn out, galaxies will drift apart, and black holes will evaporate. The universe will become a cold, dark, and empty place. This scenario is often referred to as the heat death of the universe. While the Big Freeze may seem like a bleak end, it's important to remember that it's based on our current understanding of physics. New discoveries could always rewrite our understanding of the universe's fate. The Big Rip is a more dramatic and violent end to the universe. In this scenario, dark energy doesn't just drive the expansion of the universe, but it also intensifies over time. This intensifying dark energy would eventually overcome all other forces, leading to a cosmic apocalypse. First, galaxies would be torn apart, followed by stars, planets, and even atoms themselves. The fabric of space-time would be ripped apart, ending the universe as we know it. This scenario is highly speculative, but it highlights the profound implications of dark energy. The Big Rip, if it were to occur, would happen in the distant future, long after our solar system has ceased to exist. It serves as a reminder of the vastness of cosmic timescales. The Big Crunch is a more cyclical view of the universe's fate. In this scenario, gravity eventually gains the upper hand over dark energy. The expansion of the universe slows down, stops, and then reverses. The universe begins to contract, with galaxies moving closer together. Temperatures and densities rise as the universe collapses in on itself. Eventually, the universe returns to a state of extreme density and temperature, similar to the conditions at the Big Bang. This scenario raises the possibility of a new Big Bang, creating a new universe from the ashes of the old one. This idea of a cyclical universe is appealing to some, but it remains highly speculative. The concept of the multiverse takes the idea of a single universe and expands it exponentially. It proposes the existence of multiple universes, each with its own set of physical laws, constants, and perhaps even dimensions. These universes may be completely separate from our own, existing in parallel but inaccessible regions of reality. Or they might interact with each other in ways we don't yet understand. The multiverse is still a highly speculative idea, but it has gained traction in some areas of theoretical physics. It offers a possible explanation for the fine-tuning of our universe's physical constants, suggesting that our universe is just one of many possible configurations. The expanding universe is a profound concept that has revolutionized our understanding of the cosmos. From the Big Bang to the mysterious forces of dark matter and dark energy, we've made remarkable strides in unraveling the universe's history and predicting its future. While many questions remain unanswered, our quest to understand the universe is an ongoing journey of discovery. As we continue to explore the cosmos, we gain a deeper appreciation for our place in this vast and ever-evolving universe. The ultimate fate of the universe is still uncertain, but our thirst for knowledge and exploration continues to drive us forward.